Here's a problem that's somewhat related to the elevator problem in the sense that there are moments in time when you feel heavier or lighter than your typical weight. So I want you to imagine a car that's driving at a steady speed down a bumpy highway so that it drives through some dips and over some hills. So maybe at one point when the car is at the bottom of the dip, it's still going that same constant speed. We'll say that's 30 meters per second. And you're sitting inside this car and you have a mass of 60 kilograms. Okay, so if we let G round up to 10 meters per second squared, then that means your weight, which is your mass times acceleration due to gravity, would be 600 newtons. So same car going 30 meters per second through the dip, you would feel heavier than 600 newtons as you go through the bottom of the dip. And likewise, as the car goes over the top of the hill, you would feel lighter than 600 newtons. So let's see if we can figure out why. So we can picture the curvature of the dip as being a portion of a circle. So let's give a radius of curvature. Let's say the radius of curvature is equal to 100 meters. And likewise, as you go over the top of the hill, we can also say that represents a portion of a circle, and we'll make a radius of curvature there. We'll say in this case, the radius of curvature is a little less. Maybe here it's 80 meters. Okay, so let's make a free body diagram for you inside the car when you're in this position. So let's see, gravity pulls down, mg, and as we know, that's 600 newtons. Now, there's a normal force pushing up, and you might be tempted to draw it just as big as mg going down, right? That's certainly what the free body diagram looks like for the car when it's driving across the level road. The normal force up and the weight vector pointing down would definitely be equal at this point, because driving at a constant speed in a straight line represents equilibrium, where the net force is zero. However, driving along a curved path is not an example of equilibrium, because if you follow part of a circle, then there must be a centripetal acceleration. And think of what that means. Centripetal means the acceleration has to point toward the center. So the only way the acceleration could point toward the center is if the normal force is larger in magnitude than the pull of gravity. So it's the difference between the upward normal force and the smaller downward force of gravity that presents a net upward force. The net force in this case would be normal force minus mg. Okay, so we'll take that as step one, and then in step two, we simply replace net force with ma. So ma equals n minus mg. But keep in mind, this is a centripetal acceleration. So in the next step, we can replace acceleration with v squared over r. So mv squared over r equals n minus mg. So let's solve for n. N is equal to m times the quantity v squared over r plus g. Well, this is what you feel. You feel the amount of contact force with your seat. So you feel the normal force, which is why you feel heavier than 600 newtons. In fact, in this example, you would feel 60 kilograms times 30 meters per second squared divided by 100 plus 10. So 30 squared would be 900, right? And 900 over 100 give us 9. So the normal force would be 60 kilograms times 9 plus 10. Oh, well, I'm leaving out some units, right? This is 100 meters. So everything comes out to be meters per second squared. 60 times 19 is 1,140 kilogram meters per second squared, otherwise known as newtons. Okay, so in this case you would feel almost twice your typical weight. So maybe the numerical values I made up were a little bit ridiculous, right? This might be a rather small radius of curvature for roads that have speeds at 30 meters per second. Anyhow, as you go over the top of the hill, a similar scenario takes place. Now, there's going to be no difference whatsoever in your weight vector. No matter where you are, you weigh 600 newtons. So the length of this vector mg is exactly the same when you're on the top of the hill as it is when you're going through the bottom of the dip, as it was driving on level ground. mg is 600 newtons. But that's not what you feel. You feel the normal force. And if you're tempted to draw the normal force the same length as the vector mg, then you've got the wrong idea. There has to be a net downward force. After all, you're not in equilibrium because you're not traveling in a straight line. There's only two possibilities for equilibrium. Remember, at rest is one case of equilibrium, and the second case is constant velocity. That means constant speed in a straight line, but driving through a curve is not a straight line path. So there is a centripetal acceleration as you go over the top of the hill, which means the normal force must be smaller in magnitude than mg, so that the net amount of force points downward. So this time the net force is mg minus n, right? Through the bottom of the dip, we said the net force is n minus mg. Here we're saying the net force is mg minus n. We can replace net force with ma, but this is a centripetal acceleration, so mv squared over r equals mg minus n. So this time we get n equals m times the quantity g minus v squared over r. So here we get numerically n is equal to 60 times the quantity 10 minus 30 squared divided by, what did we say? Oh no, 80. So we get normal force is equal to 60 kilograms times 10 meters per second squared minus 11.25 meters per second squared. Uh-oh, that means we're going to have a negative normal force. Well, that can't be. So the numbers I made up are unreasonable. You wouldn't possibly be able to drive 30 meters per second if the radius of curvature was this small. So we ask the question a different way. We say, what's the maximum safe speed you could have if the radius of curvature was 80 meters? So this result we get is still the correct algebraic result. We just picked unreasonable numbers for the speed and the radius of curvature. So as a car drives over the top of a hill, we ask, what's the maximum safe speed given some radius of curvature? And it works out that the normal force is equal to m times g minus v squared over r. So the free body diagram has forces in opposite directions, n and mg, and n is definitely less than mg. Well, what's the smallest possible value you could have for n? I guess the smallest possible value is if n goes to 0. so that your free body diagram is just mg. Now that could work because we notice mg is a force that points which way? Yeah, toward the center of the circle. So as long as there's something to provide a centripetal force and allow for this centripetal acceleration, you're set. So this would be a case where you wouldn't have to rely on any amount of normal force. So if the normal force goes to 0 in the limiting case, then that means m times g minus v squared over r has to go to 0, which means g minus v squared over r would have to equal 0, or in other words, v squared over r would equal g, so v would be the square root of gr. So in this example, v would be the square root of, oops, I was going to say 9.8, but we rounded up, 10 meters per second squared times 80 meters. So this is the square root of 800 meters squared per second squared. Which comes out to about 28.3 meters per second. So at 30 meters per second, the car's going a little too fast to be able to go over the hill. And you know what would actually happen then? If the car drove any faster than 28.3 meters per second, it wouldn't follow a curve of this radius. It would end up going airborne and crashing into the ground here. Okay, so just one more example of how we make free body diagrams, apply Newton's laws, and in the case of centripetal acceleration. Thanks for watching.